Bismillahirrahmanirrahim. Assalamu alaikum, students. In the last lecture, we discussed certain troubles with classical physics. We discussed the trouble with our idea of time, with our idea about length, and the trouble with our ideas about velocity. We discussed the trouble with our idea about light. We discussed Einstein's paradox. Today, our topic is the postulates. I write the postulates of spatial relativity. So this is our topic for today. You know, any scientific theory usually begins with general statements. Now, those general statements are called postulates, right? And these postulates attempt to provide a basis for the theory. From these postulates, we can obtain a set of mathematical laws in the form of equations that relate physical variables. Finally, we test the predictions of the equations in the lab. The theory stands until contradicted by experiment, after which the postulates may be modified or replaced, and the cycle is repeated. As we already discussed, for about 2 centuries, the mechanics of Galileo and Newton withstood all experimental tests. In this case, the postulates concern the absolute nature of space and time. Now, based on his thought experiment about catching a light beam, as we have already discussed, Einstein's paradox, Einstein realized the need to replace the Galilean laws of relative motion. Now, in his 1905 paper, scientific paper, entitled, the title of that paper was on the electrodynamics of moving bodies. Now, in this paper, Einstein offered two postulates that form the basis of his spatial theory of relativity. Now, we can rephrase his postulates as follows. Let me use another color. One of the postulates is called the principle of relativity. Principle of relativity is our first one. it says the laws of physics are the same for, I should write this way, are the same in all inertial frames of reference. This is one postulate, the principle of relativity. I repeat, the laws of physics are the same in all inertial frames of reference. Now, the second postulate is the principle of the constancy of the speed of light. The principle of the constancy of the speed of light. What does it say? It says the speed of light in free space has the same value as the same value c in all inertial frames of reference. It's our second postulate. The speed of light in free space, or you can say vacuum, has the same value c in all inertial frames of reference. Now, the first postulate, as you can see, declares that the laws of physics are absolute, universal, and the same for all inertial observers. Laws that hold for one inertial observer cannot be violated for any inertial observer. The second postulate is much more difficult to accept because it violates our common sense, which is firmly grounded in the Galilean kinematics that we have learned from everyday experiences. We have already discussed the Galilean law of velocity transformation, according to which a projectile fired from a moving car has a velocity related to the ground determined by the vector sum of the velocity of the projectile related to the car and the velocity of the car related to the ground. However, the velocities of light, waves, and particles moving at speeds close to c do not behave in this way. We will discuss in coming lectures the relativistic law for velocity addition and show that it reduces to the common sense Galilean law of velocity transformation at low speeds, right? Now, Einstein put forth these postulates at a time when experimental tests were difficult or impossible. During the following decades, the development of high energy particle accelerators made possible the study of the motions of particles at speeds close to c. Now, in 1964, for example, an experiment was performed at CERN. You know CERN, the European High Energy Particle Physics Laboratory near Geneva, Switzerland. The proton accelerator at CERN was used to produce a beam of particles called neutral pions. Neutral pions. We have already discussed pions, which is denoted by pi naught, which decay rapidly with an average lifetime of about 10 raised power minus 16 seconds into 2 gamma rays. This process of decay of neutral pions into 2 gamma rays can be written as neutral pion gives 2 gamma rays. Now, gamma rays, as you know, are electromagnetic radiations that travel at the speed of light. The experimenters measured directly the speed of the gamma rays emitted by the decaying pions, which were moving at the speed of 0.99975 c. See the speed of light in vacuum, right? I repeat, the experimenters measured directly the speed of the gamma rays emitted by the decaying pions, and the decaying pions were moving at speed of 0.99975 c. Now, according to Galileo, gamma rays emitted in the direction of motion of the pions should have a speed of c plus 0.99975 c is equal to 1.99975 c. In the laboratory frame of reference, right? According to Einstein, they should have a speed of c. Now, the measured speed was equal to c, to within 1 part in 10 raised power 4, thus providing direct verification of the second postulate, right? Now, the two postulates taken together have another consequence. They imply that it is impossible to accelerate a particle. I should write, it is impossible to accelerate a particle to accelerate a particle to a speed greater than C. No matter no matter how much kinetic energy we give it. Should remember it. I said these two postulates taken together have this consequence that they imply that it is impossible to accelerate a particle to a speed greater than c, no matter how much kinetic energy we give it. This is also a prediction that can be tested in the laboratory, and one that brings out another difference between the postulates of relativity and those of classical physics. Now, classical physics places no upper limit on the speed that an object may attain. Relativity does impose such a limiting speed, which by the first postulate must be the same for all frames of reference. Now, in another experiment in 1964, electrons were accelerated. Electrons were accelerated by a large voltage difference up to 15 million volts, right? And the speed of the electrons was directly determined. I will draw a figure which shows the measured speeds in this experiment as a function of the kinetic energy acquired by the electrons. Let me draw the figure first. I think I should use next page. The diagram or figure goes like this. Let me draw it, then I will explain it. Here I have 0, then I have 5, then I have 10, now 15. Kinetic energy in million electron volts. On this side I have speed in meter per second. It is 3 into 10 to the power 8. It is 2 into 10 to the power 8. Let me use some other color. Let me use some other color. This one. No, this. This is speed is equal to c. This is classical. This is relativistic. So in this figure, what you see, as I have already told, that an experiment was done in 1964 in which electrons were accelerated by a large voltage difference up to 15 million volts, and the speed of the electrons was directly determined. Now this figure shows the measured speed. You see on y-axis we have speed of these electrons in meters per second, and on x-axis we have kinetic energy acquired by these electrons in million electron volts. Now you can see from the figure, no matter how much the accelerating voltage is increased, the speed never quite reaches or exceeds c. Now in classical theory, this blue curve shows the classical theory. There is no speed limit, but relativity puts a speed limit. Red line shows the relativistic curve. Now you can see from the figure, let me show the measured values. The points, these black points, which are the measured values of the experiment, they fall on the relativistic curve. That means the speed never quite reaches or exceeds c. So once again, experiments at high speeds are inconsistent with predictions based on the kinematics of Galileo and Newton, but instead confirm the postulates of spatial relativity. Right? So this is the triumph of Einstein and his theory. Let's move to next thing. Our next topic is the consequences of Einstein's postulates. This is our next topic, right? Now in last lecture, we discussed the difficulties in interpreting certain measurements of time, length, and velocity based on classical physics. Now we want to discuss or study how Einstein's postulates can resolve those difficulties. Now, first, we discuss the relativity of time. The relativity of time. So listen carefully. Now we consider two observers. S is at rest on the ground and S prime is in a train moving on moving on a long straight track at constant speed u relative to s, right? So we consider two observers. I repeat, one observer is S, second observer is S prime. Now S is at rest on the ground and S prime observer is in a train moving on a long straight track at constant speed u relative to S. The two observers carry identical timing devices. The two observers carry identical timing devices. Depicted in figure 2. I've already used figure 1. Let me show diagram to indicate our timing devices. It's like this. Use another color. This one. This is the timing device. Now what is it? Let me illustrate. Now the timing device shown in figure 2, which both observers carry, consists of a flashing light bulb F. So F is a flashing light bulb, and attached to it is a detector D. So D is a detector, F is a flashing light bulb. And they are separated by a distance L naught from a mirror M. So M is a mirror. And distance between the uh, detector and flashing light bulb and the mirror is L naught. Now how our timing machine clicks or ticks, actually what happens, the bulb emits a flash of light that travels to the mirror as shown in the figure. What will mirror do? It will reflect that. Now when the reflected light returns to detector D, the clock ticks. I repeat, the bulb emits a flash of light. That light travels to the mirror. When the reflected light returns to D detector, the clock ticks and another flash is triggered. Now the time interval delta T naught between ticks to consecutive ticks is just the distance 2L naught covered by the light or traveled by the light divided by the speed of light c, right? So I name it equation first. This is my equation first. I have not used any number for an equation in this lecture. So this is our equation first. So what is delta T naught? Delta T naught is the time interval between two consecutive ticks. It is simply the distance 2L naught, that is the distance traveled by the light in round trip, divided by the speed of light c. Now the interval delta T naught, I should write it, the interval delta T naught is observed by either S or S prime when the clock is at rest with respect to that observer. I write it is important. The interval delta T naught is observed by either S or S prime when the clock is at rest with respect to that observer, right? That means delta T naught will be observed by S if the clock is at rest relative to S. Delta T naught will be observed by S prime if the clock is at rest with respect to S prime. We now consider the situation when one observer looks at a clock carried by the other. Let me show another figure first. I will draw a figure first, then I will explain. You can draw the figure. This is mirror. Use another color. Let me use this one. We enclose it. So this color now. This is B, this is C. We complete the figure. So let me name this figure first. Figure 2, no, figure 3. This one, figure 3. Figure 3. So let me explain this figure. Now in this figure, in the frame of reference of S, remember S is staying on the ground. We have already discussed S is at rest on the ground. Now in this figure, in the frame of reference of S, the clock carried by S prime on the train moves with speed u, right? Now this dashed line of length 2L overall shows the path of the light beam according to S. I repeat, we are now considering the situation when one observer looks at a clock carried by the other. Now in this figure is shown in the frame of reference of S. What it shows from the point of view of S, the clock carried by S prime on the train, which is moving with speed u, and the dashed line of length 2L shows the path of the light beam according to S, right? So this figure 3 shows a representation of this sequence of events that S observes on the clock carried by S prime on the moving train. According to S, the flash is emitted at A, reflected at B, and detected at C. We have separated the overall round trip of the light into 3 instants. At A, according to S, flash is emitted. At B, the flash is reflected. And at C, it is detected by the detector. Now, in this interval, we call now this interval delta t according to S. Now, in the interval delta t, according to S, the clock moves forward a horizontal distance u delta t, because S is sitting on the ground. So according to S, S prime is moving with u, so does the clock carried by S prime. So in delta t interval, in which this round trip is completed by the light beam, according to S, the clock has moved distance u delta t, right? horizontally from the location where the flash was emitted. So according to S, the light beam travels a distance 2L, where L is what? What is L? In order to find the L, you have to make here a right angle triangle. If I make a right angle triangle, I will show you it approximately this way. If you make this right angular triangle, right, this is overall u delta t, it will be half u delta t. So what will be L square will be L naught square. Remember, this is L naught. So this is using Pythagoras theorem. L square will be L naught square plus half u delta t square, right? So L square will be L naught square plus half u delta t square. So I've simply used the Pythagoras theorem. So according to S, let me move to the next page. According to S, the observer on the ground, the light beam travels a distance to L, where L is under root L naught square plus u delta t by 2 square, whole thing in the square root. It is simply L square is L naught square plus half u delta t square. L will be square root of this. We have written that L naught square plus half u delta t square, as shown in the figure. Now the time interval measured by S for the light to travel this distance at speed c, let me write it, the time interval measured by S for the light to travel this distance at a speed c. Remember, the same speed measured by S prime, which is the postulate, is delta t is 2L by c, which is 2 L is L naught square plus u delta t by 2 square then over c, right? Delta t is 2L by c is 2 times under root L naught square plus u delta t by 2 square, whole thing in the square root, overall divided by c. Let me name it second. I name it second. Remember, our first equation is this one. Delta t naught is 2L naught by c. So solving, or sorry, substituting for L naught from equation 1. From equation 1, what is L naught? C delta T naught over 2. So I write, next page, substituting for L naught from equation 1 and solving equation 2 for delta T gives, substituting for L naught from equation 1 and solving equation 2 for delta T. This is our equation 2. So we solve it for delta T using equation 1 for L naught. So what we get delta T is delta T naught over under root 1 minus u square by c square. I encircle this result. It is important. I name it equation 3. You check it at home. Check it at home. That when we substitute for L naught from 1 and solve for delta T from equation 2, we will get delta T for delta T naught over under root 1 minus u square by c square. Now the factor in the denominator, that's under root 1 minus u square by c square, is always less than or equal to 1. And thus delta T is greater than or equal to delta T naught. Important. Delta T is greater than or equal to delta T naught. That is, the observer relative to whom the clock is in motion, in our case observer S, measures a greater interval between ticks. This effect is called time dilation. Now the time interval delta T naught measured by an observer S prime in our case relative to whom the clock is at rest is called the proper time, right? Now the proper time interval between events is the smallest interval between them that any observer can measure. All observers in motion related to the clock measure longer intervals, right? Now equation 3, this one, enables us to understand the difficulty with the pion decay experiment which we discussed in the last lecture. We said pion at rest decays in a time interval of 26 nanoseconds. Now this interval is a proper time interval and is designated by delta T naught. Remember, the pion is in effect a clock, and the interval from formation to decay of the pion can be regarded as a tick of the clock. Now, an observer in the laboratory, relative to whom the pion is in motion at a speed of u equal to 0.913 c, would be expected to measure a time interval delta t equal to delta t naught over 1 minus u square by c square. Remember equation 3. So we make the substitution. Let me use another color. My delta t naught proper time interval is 26 nanosecond, and I have in square root downstairs 1 minus, when I put the value of u, I will get simply c square will cancel out. It will be 1 minus 0.913 square, right? When you solve it, you can check it. It turns out to be equal to 63.7 nanosecond. 63.7 nanosecond in agreement with the measured value, right? Now equation 3, which is deduced from Einstein's postulates, gives the relationship between time intervals, acquired time intervals according to spatial relativity for observers in relative motion. Note that the factor in denominator under root 1 minus u square by c square differs appreciably from 1 only at speeds that approach the speed of light. At ordinary speeds, right, at ordinary speeds, we can take delta t equal to delta t naught to a very high precision. This is the classical result, which is obtained directly from equation 3 in the limit u much less than c, and is in accord with our common sense experience. Now remember, equation 3 is valid for any direction. I should write it. These are some important points. Equation 3 is valid for any direction of the relative motion of S and S prime. It is also valid for any type of clock, not just the spatial one we used in this derivation. It has been experimentally verified not only with decaying elementary particles such as the pion moving at high speed, but also with precise atomic clocks moving relative to one another at ordinary speeds. Even biological clocks, bio law, important biological clocks such as human aging are expected to be affected by time dilation. Right? I repeat, even biological clocks such as human aging are expected to be affected by time dilation. Now, an interesting aspect of this effect is called twin paradox. We have to discuss that in coming lectures. Very interesting twin paradox. Right? Now, this is all for today. We are going slowly. Don't waste your time. Make notebook. Learn at your own pace all the video lectures. Right? And do not forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.